my name is Emily Downing. My project is coupling paradynamics and linear elastic models with a changing stiffness constant with my mentors Patrick Deal and Sergey Prudhomme. Just for some background, paradynamics is a non-local model of damage and deformation that is a form of continuum mechanics, and we're specifically focused on bond-based paradynamics, which is about the points and how they interact with each other. We also have linear elasticity, which is a linear relationship between stress and strain that can't have yielding, which is when material reaches a point which it can no longer stretch and it has to deform or break itself. It can't, that by definition, linear elasticity can't do that. The reason we're looking to couple them is because paradynamics is very accurate, but it's also very costly and very inefficient. Whereas linear elasticity is not, it runs much more efficiently. So by using paradynamics in the spot where there would be a break, we can combine the benefits of both models together. So this is a look at our coupling model. As you can see, we have the black dots, which are the linear elasticity portion of our model, and the white dots, which represent the paradynamic model, with the difference between each point being delta, which I'll get to later. And we use the paradynamic model in the center where there would be the break, and then the linear elasticity around it, because when a material does break, you still usually have pieces which could be represented by linear elasticity because they themselves are not breaking. So what we accomplished this summer is there was already code in which they were coupled using the matching displacements method, which just means they were in the same spot. They met up at the same spot. And we added a changing stiffness. Specifically, it got lower to a value that you would input, starting at 1, going down to the value that you inputted, and then back up to 1 before entering the linear elastic section. And then we also added an alternate approximation method to calculate the final difference for our error functions, because before we were comparing our function to a graph that was before the damage was put in, which didn't match and was giving us nonsensical values. So our results, the graph on your left is the two displacements of the actual model and our approximation, the black being the actual model, the red being the approximation, and the right being the difference between them at the same scale. This first example is if you had a one-dimensional object where one endpoint is fixed, and then you pull it on one side at each point. You'll notice that there are different delta values for 4 different graphs. This just means we had a different number of points in each of our runnings of the simulations, the denominator being the number of points, and this matters because that's the number of steps it takes before the stiffness goes down and then back up again, and it gives us a different resolution for the points. This is the second case we had where both of the endpoints were remaining fixed, but there was force pushing them towards the center where they would reach 0. And again, on the left, we have the displacement graph, and on the right, we have the difference between them. And you can see it more in this graph where the difference of the delta comes into play, with the graph on the bottom being the largest delta or the smallest number of points, and the graph on top being the largest number of points. You'll notice that the difference graphs is very small, which means that our graph is probably right, which means that it can handle the stiffness getting lower in the center, which means in the future, actual damage could be put in so that the model could actually function.
Questions?
The second slide that you had with the graphs.
Yeah.
Do you? Oh, sorry. The second one that had like the two plots. The second of those two. Yeah, that one. Is it known why exactly like at that x value right there, like a little bit higher than 1.5, like why that's where the curves really differ? Or is there any reason why it happens at that specific x value?
I assume it's because that's where it starts to get less stiff.
Okay.
Because it's not right at this point that it gets less stiff, because otherwise it would be messing with the linear elastic, because the linear elasticity goes from 0 to 1. So we have a little bit of a buffer before it actually starts to go down and then come back up again. So I assume that that being different is what causes that.
More questions?
What's the FDM on the right graph again?
The FDM?
On the axis?
Oh yes, that's a final difference method. This just means that it's the subtraction of these two lines, specifically the black one minus the red one.
Okay.
Does material density have any impact on your graphs?
Not yet.
Oh, yeah.
That will be included in the future.
I gotcha.
Okay, I have, could you show the previous, I have the same question. I mean, 25, you have there a displacement of 25, but in the horizontal is, you have 3.
Yes.
So this means a huge displacement, or, I mean, how do you correlate the 25 with the 3 in the horizontal?
It would be a large displacement. It's larger than it would be if there wasn't the changing stiffness, because it's getting softer. It's moving a lot more in the middle, which then means the end has to move a lot more because it's moving with the center and then it moves on its own. But specifically we were more looking for the shape, because this is the shape that we want the graph to make with the force. So that's more what we were focusing on.
Okay. So it doesn't mean that the end point finish at 25, finish 6 times farther the distance, doesn't mean that.
Yes, they're not actual values.
Are not in the same unit.
No.
Thank you. Any other question? Okay, so thanks, Emily, again.